Alright, so in order to really talk about motion, we have to first talk about where something is in the physical world, and that's where position can help us. So we need to look at a frame of reference in order to do that, and that could be Earth, and for the most part that's going to be Earth. So first things first, what you want to write down from this slide is the definition of position. Position is where something is at any particular time. So with that, we need to figure out frame of reference, which could be Earth, and that's our common frame of reference. It could be if we're looking at something moving inside of something else moving, like a plane, and someone moving, or a car driving down the road, and a ball being thrown up and down inside of that car. That could mean that our frame of reference needs to be the car then, instead of Earth, because of the motion of that object inside of the car. It's going to behave more as if the car was standing still, even though it's not. It could be moving, but that ball's motion to the people that are inside of that car is like as if it was standing still. Um, so that's how frame of reference works, and that's what we need to start with and use position with the coordinate system. And the advantage for physics is that we can set that coordinate system up however we want to. So we can adjust it to how we need it. So for this slide, taking in position, we also need to take into account displacement. And this is just the change of position of an object. And so there's a formula for that. So bringing in our good friend, the Greek letter delta, to represent change in. So change in x, or change in position, is equal to the final position minus the initial position. So we use that symbol 0 as our subscript for initial instead of I, because I is used too many times already. So instead of using it again here, we branch out and use I instead, or not I instead, we use the 0 instead, and that 0 just represents, we call it x naught in this case. It could be v naught later on when we're looking at velocity, but is always going to represent the initial of whatever thing we're talking about. In this case, that's the initial position. So we have this image here that is representing motion in one direction. So you're going to want to draw that picture so you have an idea as to how positive motion works, positive displacement specifically. And so this professor is walking 2 meters in one direction. She's moving to the right. And in this case, again, another picture. You're going to draw that one as well. And this time the person on the plane is moving 4 meters to the left, and left is negative. So that means that it's a negative displacement. Displacement has both magnitude and direction. And it is a special kind of quantity that we'll talk about in just a moment. So this slide here just talks about the two ways that displacement can have positive and negative two directions, especially in one-dimensional motion. Here we have a question. Which of the following words implies that an object has moved or has been displaced? Well, of course, that's displacement. This one here, displacement has a direction, it has a magnitude. It has both. It has a direction as well as a magnitude. From this slide, you're going to want to take the definitions that are given here. So the definition for distance, which is that is the magnitude of displacement between two positions. And then the definition for distance traveled as well, that is going to be the total length of the path traveled between two positions. Distance has no direction, so neither one of those have direction, as did displacement before, and that's a big deal. And that's where this misconception could come in. Your distance traveled and magnitude of displacement are both going to have no sign, and that's because the magnitude of displacement sign has been taken away. But they are not always going to be the same thing. They can be, the same measure, but they won't always be the same measure. And that is where people can get tripped up, is that those two things seem like they're going to have the same quantity, same value, but they don't always have the same value. It depends on how the motion occurs. So if somebody moves positions and their displacement is 0, well, the magnitude of displacement is also 0, but they may have actually moved somewhere. They just ended up back to the exact same starting position that they were in before. So here we have an example. The cyclist rides 3 kilometers west and then turns around and rides 2 kilometers east. So first off, we have to draw the vector. We use arrows to represent vectors. The 2 image slides from before mentioned that. So we have this negative 3 kilometers because it's going west. West is to the left, so that is negative. Then we have a positive 2 kilometer motion to the east after she turns around and rides back the other way for 2 kilometers. So we set up our coordinate system to where starting position 0, move negative 3 to the left, and so then within that we have these 2 breaking points at negative 1 and negative 2, and so this is our displacement because that is the difference between the starting point and the ending point. So the formula for that, again, delta x, or change in x, is equal to the negative 1 that we ended up at, and minus 0. Remember, that is the final minus initial, or x naught. And so negative 1 minus 0, that's just equal to negative 1 kilometer. For part B here, we're looking for, it says distance, but we're going to go ahead and find the distance traveled instead. There's a reason for that, and that is that part C is finding the distance, or the magnitude of the displacement, and that's the same thing as distance. So that's the definition of distance. So here, distance traveled, she went 3 kilometers in one direction, then 2 kilometers in another direction, totaling 5 kilometers. But for part C, we haven't really talked about how to find the magnitude of displacement, and that has to do with the absolute value of the displacement. So we know our displacement is negative 1 kilometer. We got that for part A. So we're looking for that absolute value of that displacement here. And remember, absolute value just is the distance away they are from 0. So if it's negative, it gets rid of the negative sign. So negative 1 becomes 1 kilometer. So you can see here all 3 things, they are different numbers, different measures, and they all are related to the exact same problem and the same exact motion. So even though we're really talking about one person's motion, these 3 different things about distance and displacement and measures of length give us different things. So here we got under what circumstances, well, we got 2 questions here. Well, under what circumstances does the distance traveled equal the magnitude of displacement? And the only way that's going to happen, remember, magnitude of displacement is the absolute value of the displacement. So if that means that the magnitude of the displacement is equal to the distance traveled. The only way that's going to be possible is if they are going in the same direction and there is no change in direction. The second question here, what is the only case in which the magnitude of displacement and the displacement are exactly the same thing, is if they are moving in just the positive direction. Because if you go negative at all, or if you just have an overall displacement that's negative, then the magnitude of the displacement is going to be a positive version of that and not including the negative version of it at all, which is what the overall displacement would be. So if the overall displacement is negative, it's not the exact same thing as having a positive displacement, or positive magnitude displacement. So here we got some definitions again. So looking at them, you can move those sliders around. Obviously there's a video instead of the actual nearpod, so we're just going to go through it here. So first definition is the magnitude of displacement between 2 positions. So of these options, that's distance. the total length of the path traveled between two positions. Well, that's the total length traveled. Key word there, traveled. So that is the distance traveled. And our next definition is the change in position of an object. That's displacement. And finally, the only thing left is the study of motion without considering its causes is the definition of kinematics. That's the unit we're in right now. That's Unit 1. We will look at the study of motion with its causes, and that's going to be dynamics. That's our next unit. This slide, there's nothing to write down. It's pretty much just talking about how displacement has that magnitude and direction, and that means it is called a vector. And here we have the definition of a vector. So a vector is a quantity that has both magnitude and direction. It's a special type of quantity that has those two things involved. And there's a few examples here. Velocity is a vector, force is a vector. There are many other things that we'll talk about throughout this course that are vectors. We also represent them graphically in every type of dimension that we can talk about. We're going to do 1 and 2D. But we use arrows to represent them. The length is proportional to the magnitude, and they point in the directions that the vector is going in. Scalars are quantities that just have magnitude but no direction. So temperature, energy, speed, height, distance, those are all scalar quantities. You just have to be careful because temperature can be negative. Remember, that just means it's a distance away from zero, but not that is indicating a direction that's involved. So we're going to skip that, but here we have that acceleration is the change in velocity over time. So given that, does that mean that it is a scalar? We already mentioned that, actually I didn't mention the acceleration when we were looking at the last slide, but really anything that you take a vector and you do some math to it with just a scalar typically, so a vector divided by a scalar or a vector multiplied by a scalar, you're going to get another vector out. We already mentioned that velocity is a vector, so a vector divided by scalar time, that's going to give you a vector back out. So that means that acceleration is indeed a vector. It does have direction, it does have magnitude. Its sign is a little bit funky, and we'll take a look at that in another video later, or another notes later on, but we'll get there. So kind of skipped through that slide on accident there, but this slide just talks about how we set up our coordinate system in one dimensions, usually left and right. Left is negative, right is positive, up is positive, down is negative, and same for the slide here, just as a graphical representation of exactly that. It's our normal Cartesian system, basically, but only looking at one axis at a time. So one more time, we got another question here. A person's speed can stay the same as he or she rounds a corner and changes direction. Given this information, is speed a scalar or a vector? So if the speed is staying the same, but the direction is changing, that means it can't be a vector. It has to be a scalar. Remember, the direction is part of a vector. So if any part of the vector is changing, the vector is changing. So if the direction is changing, the vector is changing. Even though the number might be staying the same there, the vector is changing. So if a scalar, if speed is a vector, it's not, then if its direction is changing, well, its vector is changing, and that's not what it says here. The speed is staying the same. So if the speed is staying the same while the direction is changing, speed is a scalar. And this next slide is just going to give us that exact answer. So speed is a scalar quantity, it does not change direction, or change at all with direction changes. This slide just talks generally about motion. We're not going to really talk much about it here with this slide, but we are going to see some things about it. So what was runner speed? How long does it take to a foot race take? And these things are important, but without them, before we talk about those, we need to talk about time. And time is change. That's the definition that we have here that we want to write down. Time is change, or the interval over which change occurs. And really, it's impossible to know that uh, change is occurring or that time has passed without knowing that something has changed. So that's a big important part there. So make sure you jot that down because it's important to have these definitions down. We will study them again later with Quizlet as well. So correlation between time and motion, that is looking at how time has passed, and that is using elapsed time. So elapsed time is the difference between ending and beginning time, and its formula looks pretty similar to displacement, right? We got change in time is equal to time final minus time initial, and again, T naught is here. Now, for our cases, mostly, we can set up things to ourselves so that we can make that initial time T naught be 0. So when that occurs, it makes it so there's really nothing to do. Whatever time was given to us that had elapsed is given to us instead of, or whatever final time that we are given is our elapsed time as well. So we started at 0 and ended with our time. And this again just talks about that T naught typically is 0. There's another collaboration slide where we're going to skip over, but this one here just talks about how velocity works, and you probably know it as the scientific definition, but here is a specific definition for a type of velocity called average velocity. You're going to want to write this one down as well. Average velocity is displacement over the time of travel. And write down the formula, make sure you have that. And I'm going to go ahead and move that bottom formula up so it's all together. So if you want to write it like that, that would be a good idea. And again, the reason it changed is because D naught is typically equal to 0. So since that occurs, we can just ignore the subtraction part on the denominator. This one refers back to the airplane picture that you drew. So the negative sign in the displacement transfers over to being a negative sign for the velocity as well. So his movement back to the back of the plane is negative for the displacement, so his velocity was also negative, specifically negative 0.8. But it doesn't bring into account the fact that his motion may not have been consistent. It doesn't tell us anything about his motion other than the fact that he moved negative 4 meters backwards. Well, did he do anything in between? And that's kind of the downside to displacement as well. It doesn't really talk about that. So that's where we talk about instantaneous velocity. Instantaneous velocity is the average velocity at a specific instant in time or over an infinitesimally small time period. So write that one down. And unfortunately, mathematically speaking, in order to be very precise with instantaneous velocity, you have to use limits, which are in calculus. This is algebra-based physics, so we are not going to do that. We have to be given some specific information to do that. So here we have an example problem. A commuter train travels from Baltimore to Washington, D.C. and back in 1 hour and 45 minutes. The distance between the two stations is approximately 40 miles. What's the average velocity between the train? It's 0 because a little bit faster on the slides now, but it's 0 because they end in Baltimore after starting in Baltimore. Here, instantaneous velocity is the velocity of the specific instant. Displacement within a certain time is average velocity. Difference between ending time and beginning time is elapsed time, and the interval over which change occurs is the definition of time. Whew. But going back to that last problem, it was asking for average velocity. So even though we're given the distance between Baltimore and Washington, D.C., we don't care. We are dividing 0 by something. So So just like we have instantaneous velocity and average velocity, we also have instantaneous speed and average speed. Instantaneous speed is the magnitude of instantaneous velocity, and average speed is the distance traveled between, or distance traveled divided by the elapsed time. So instead of taking the displacement and dividing by time, you're taking the distance traveled and dividing it by time. And that's the difference here listed out. And so this one actually does apply a real world situation. So we have a car traveling from the home to their house to the store and then back. Their displacement 0 because they go back in the house, and here's an image of it. But their distance traveled is 6 kilometers because they went 3 kilometers there and then 3 kilometers back. So the average speed is 0 divided by 6, which is 0 divided by half an hour, sorry, 0.5. Here's some graphical representations of these as well. So position versus time, velocity versus time. You can see how these graphs are different and how they still match up a little bit. But the average speed 0 because the displacement is 0. Displacement divided by time is average speed, so 0 divided by whatever the time is 0. And that's the middle part of all of these graphs, is the turning point. So it's kind of indicating all of that stuff. So in the previous one, we saw that switch over to the negative 12, the positive and negative 12 cancel each other out to average out to be 0. But instantaneous would be looking at that graph at any particular time. And that's kind of how you can tell the difference between the two, is the instantaneous, or actually that's how you can get instantaneous without using the limits that we talked about before, that you would have to graph with calculus. So thanks for taking notes.